Good morning. I am Devisena. In this lecture, we are going to discuss about mechanical systems and its types in control systems. This topic is present in the subject control system. In this lecture, we will discuss about a mechanical translational system as well as mechanical rotational system.
Mechanical systems. A mechanical system is a set of physical components that convert an input motion and force into a desired output motion and force. The process part of the system is where mechanisms are used to convert the input motion and force into an output motion and force. Categories of mechanical systems. Mechanical systems are classified into two categories based on the motion. They are mechanical translational system and mechanical rotational system. Translational mechanical system. Translational mechanical systems move along a straight line. The variables of this system are displacement, velocity, and acceleration. The mass, damper, and spring are the basic characterizing elements of translational mechanical systems. These systems mainly consist of three basic elements. Those are mass, spring, and dashpot or damper. If a force is applied to a translational mechanical system, then it is opposed by opposing forces due to mass, elasticity, and friction of the system. Rotational mechanical systems. Rotational mechanical systems move about a fixed axis. These systems mainly consist of three basic elements. Those are moment of inertia, torsional spring, and dashpot.
Types of forces in mechanical translation system. Three types of restricting or opposing forces are encountered in translational mechanical system, which opposes the motion of the mechanical system due to an externally applied force. They are the inertia force, damping force, and spring force, or the restricting forces that act on translational system.
Translational mechanical system representation is shown below. Here is a representation of a translational mechanical system. Here the mass is represented by an arrow indicated here, and spring is represented by this is represented as a spring. Similarly, the dashpot are represented as shown here. Inertia force F suffix m. This inertia force is due to the mass m. Mass stores the kinetic energy of the motion. When force F of t is applied to a mass m, then the mass experiences an acceleration. By Newton's second law, force is equal to mass into acceleration. That is, F suffix m is equal to m into a. The mass is represented as small m. Acceleration is represented as small a. This can be represented as capital M into d square x of t by dt square. That is equal to m into du of t by dt, where a is the linear acceleration, u of t is the linear velocity, and x of t is the linear displacement. Damping force F suffix d or F suffix b. Whenever two physical bodies are in motion, there exists a friction. It can be of three types. They are static friction, viscous friction, and Coulomb friction.
Static friction. It is observed only when the body is not in motion and its tendency is to prevent the body from moving. The direction of static friction is always opposite to the direction in which the body tends to move.
Viscous friction. It is the frictional force experienced when the body is in motion, and this force is proportional to the velocity of the body. F suffix b is directly proportional to velocity. That is, F suffix b is equal to capital B into u of t, where b is the viscous frictional coefficient, u of t is the velocity. So, F suffix b is equal to b into u of t, that is nothing but b into dx of t by dt, because the velocity is the rate of change of displacement. So we get b into u of t. A damping is represented by a dashpot system as shown below. Here is a representation of a dashpot. The dashpot experiences the velocity.
Coulomb friction. It is experienced when the body is in motion. This friction opposes the motion but has no dependence upon the magnitude of velocity or acceleration of the body. This Coulomb friction is constant in magnitude. Spring force, that is by Hooke's law, spring force is directly proportional to displacement. The spring force F suffix k is directly proportional to x. X is the displacement. Spring stores the potential energy. F suffix k is equal to k into x of t, where k is the spring constant. Velocity, we all know about that. U of t is nothing but the rate of change of displacement dx of t by dt. Therefore, x of t is equal to integral of u of t dt. So, f suffix k is equal to k into integral of u of t dt. That is, f suffix k is equal to k into integral of u of t dt. Therefore, f suffix k is equal to 1 divided by capital K into integral of u of t dt, where spring constant is nothing but 1 by compliance, where K is the spring constant and capital K is the compliance. Here we have related the spring constant with the compliance. The compliance is the reciprocal of the spring constant. So, small k is equal to 1 divided by capital K. That is, the spring constant is equal to 1 by the compliance. Therefore, f suffix k is equal to 1 divided by capital K into integral of u of t d of t. Spring damper mass system representation is shown below. This is the representation of the spring mass damper system. We know that the spring experiences displacement. Here is a representation of the spring. The spring experiences the displacement x of t, and we know that the damper experiences the velocity. Here is a representation of the damper. The velocity is nothing but rate of change of displacement, and the mass experiences the acceleration. Here is a representation of the mass. The acceleration is nothing but the rate of change of velocity. D'Alembert's principle for translational mechanical system. It states that for any system, the sum of externally applied force and the forces restraining motion in any given direction and at any instant is 0. Here is a representation of a mass spring damper system, a translational mechanical system. We are going to analyze. Applied or external force is equal to F of t. The opposing forces available in the translational mechanical system are inertia force due to mass is F suffix m. Its value is minus capital M du of t by dt. This minus sign indicates that this force is a opposing force. Similarly, damping force F suffix b, its value is equal to minus b into u of t. This minus sign indicates that the damping force F suffix b is opposing to the applied or external force. Similarly, the spring force F suffix k is equal to minus 1 divided by k into integral of u of t dt. Here also the minus sign indicates that the spring force opposes the applied or external force. By D'Alembert's principle, the sum of force is equal to 0. That is f of t plus f suffix m plus f suffix b plus f suffix k is equal to 0. Here, if you substitute the values of f suffix m, f suffix b and f suffix k, means we get f of t minus capital M into du of t by dt minus b into u of t minus 1 by k into integral of u of t dt, that is equal to 0. That is f of t is equal to capital M du of t by dt plus b into u of t plus 1 by k into integral of u of t dt. The above equation is referred as D'Alembert's basic equation for translational mechanical systems. Rotational mechanical system. Rotational systems are similar to translational system except for the basic difference that torque equations are written in place of force equations and that the displacement, velocity, acceleration terms are angular quantities. The property of system which stores kinetic energy in rotational system is called inertia. Inertia torque, damping torque, spring torque. These three are opposing torques developed on rotational system. Rotational mechanical system inertia torque derivation is shown below. Inertia torque is represented as T suffix j. This T suffix j is proportional to the angular acceleration. That is, T suffix j is directly proportional to d omega of t by dt. This can be represented as T suffix j is equal to j into d omega of t by dt, where j is the proportionality constant. This d omega of t by dt is the angular velocity, can be represented in terms of angular displacement. So we get T suffix j is equal to j into d square theta of t by dt square. That is T suffix j is equal to j into d omega of t by dt. That is j into d square omega of t by dt square, where j is the moment of inertia, theta of t is the angular displacement, and omega of t is the angular velocity. Here is the diagram that represents the inertia torque. Rotational mechanical system damping torque representation. Damping torque T suffix b. This damping torque is proportional to the angular velocity. That is, T suffix b is directly proportional to omega of t. This omega t is the angular velocity. That is, T suffix b is equal to b into omega of t. This angular velocity can be represented in terms of the angular displacement. That is, velocity is nothing but the rate of change of displacement. So we get b into d theta of t by dt. Here is a representation for the damping torque. Rotational mechanical system spring torque derivation. Spring torque is proportional to the angular displacement. That is T suffix k is directly proportional to theta of t. That is T suffix k is equal to small k into theta of t. So T suffix k is equal to 1 by capital K into integral of omega of t dt, where spring constant is equal to 1 by compliances. That is K is the spring constant, capital K is the compliance. So small k is equal to 1 by capital K, where omega of t is nothing but the angular velocity is equal to rate of change of angular displacement d theta of t by dt. Therefore, d theta of t is equal to omega of t into dt. So, theta of t is equal to integral of omega of t dt. Here is a representation of the spring torque. Rotational mechanical system representation is shown below. Here is a representation. The diagram comprises of that inertia. This inertia experiences inertia torque, and that damping experiences that damping torque, and the spring experiences the spring torque, and the angular displacement is theta of t. Applied forces the torque T of t. D'Alembert's principle for rotational mechanical system states that for any body, the algebraic sum of externally applied torque and the opposing torques at any instant is 0. Consider the following rotational mechanical system, and its motion is around a fixed axis. Applied or external torque acts on a body in clockwise direction, and opposing torque act on counterclockwise or anticlockwise direction. Applied or external torque is equal to capital T of t. Opposing torques are inertia torque T suffix j of t, that is equal to minus j into d omega of t by dt. Damping torque T suffix b of t is equal to minus b into omega of t, and the spring torque T suffix k of t is equal to minus 1 by k into integral of omega of t dt. By D'Alembert's principle, sum of t is equal to 0. That is t of t plus t suffix j of t plus t suffix b of t plus t suffix k of t is equal to 0. If we substitute the values of t suffix j of t, that is minus j into d omega of t by dt, and if we substitute the values of t suffix b of t, that is minus b into omega of t, and if we substitute the values of t suffix k of t, this minus 1 by k into integral of omega of t dt, that is equal to 0. Here this minus sign indicates that this inertia torque, damping torque as well as the spring torque experiences the opposing torques. That is t of t is equal to j into d omega of t by dt plus b into omega of t plus 1 by k into integral of omega of t dt. The above equation is referred as D'Alembert's basic equation for mechanical rotational system.
Analogous systems. Two system equations of similar form are defined as analogous system. The advantage of analogous system is if the response of one system is known, then the other system is also known without actually solving it. Generally, mechanical systems are converted into analogous electrical systems. Advantages of electrical system. Standard symbols are available in electrical system like resistance, inductance, capacitance, etc. Standard and simple laws are available in electrical system which makes it easier for calculation. Example, Kirchhoff's laws, Thevenin's theorem, etc. It is easy to analyze a system for different parameter values as an electrical system because RLC cannot only be varied but also their response can be seen. In electrical system, dual network are also analogous system, but both are electrical form. Here is a representation of a dual network in electrical system. Loop analysis and nodal analysis are dual network in electrical system. The parameters that are available in the loop analysis is listed here. Similarly, the analogous parameters in the nodal analysis are also listed here. Here is a table that indicates the loop analysis parameter as well as the nodal analysis parameter. The voltage in the loop analysis is analogous to current. Similarly, current in the loop analysis is analogous to voltage in nodal analysis. Charge in loop analysis is analogous to flux in nodal analysis. The resistance R in loop analysis is analogous to conductance G in nodal analysis. The capacitance C in loop analysis is analogous to inductance L in nodal analysis. Inductance L in loop analysis is analogous to capacitance C in nodal analysis. Here is a list that indicates the analogous system parameters.
Thank you very much for listening this lecture. If you like this lecture means kindly share this video to your friends and kindly subscribe this channel.